Recovered. So, any questions so far? Yeah.
Yeah, I kind of noticed that we're putting PDFs from lecture material after the lecture is already taking place. Are we able to start putting those PDFs before lecture so that we can just read them over and get an understanding so we can get more out of the lecture when you actually...
Sure, I can do that.
Yeah, thanks.
All right. Yeah. Okay. So, I saw last lecture, and what was there? So you guys looked at the operators, right? Again, and but then there was no really a conclusion about why they are so useful, right? So there was a connection between the observables. Any observable is actually related to operator in quantum mechanics.
Sorry, could you tell me where the Dropbox is, please?
Right now?
Yeah.
No. Wait a second, okay? So why don't we do it after the lecture, okay? It's just in general for everyone else, if you, wondering, it's generally not good to interrupt the lecture with such things which are minor, right? So we can solve them later or before. Okay, now let's focus on the operators. And of course, the main idea of quantum mechanics is to predict what would be the result of the experiment. So if we have quantum system described by a wave function, right, and we have time-dependent Schrödinger equation, allows us to know what our time-dependent wave function will be doing later time. If we know it's at time equals 0, then solving time-dependent Schrödinger equation will give us a wave function at all later time, t more than 0, right? And so say now, if we want to do some experiments, or if we want to predict from the quantum mechanics the results of the experiment, right, then we need to focus on some property. So one of the simplest, let's say, kinetic energy case, if we consider, say, electron, and we know that kinetic energy has this form, right, and more explicitly, if we put the momentum operator there, definition for one dimension, which will be slightly different for the three-dimensional world we live in, but right now, to avoid some complications related to three-dimensional world, let's just consider everything in one dimension. So that will be our operator, kinetic energy operator. And you learned in the previous lecture that all operators, they have such things as functions, which are called eigenfunctions, right? And so what are these eigenfunctions? What is so special about them?
They're functions that, once operated on, they are only changed by a constant, not which is an eigenvalue.
Right. So essentially, if we are focusing on the kinetic energy, the eigenfunction of the kinetic energy operator depends on some x. And when we differentiate twice this function, it should be the same function multiplied by some constant, right? Our typical candidate would be exponent of x times a. Right? You differentiate this twice. This will give you a square, because a will come out every time you differentiate. Right? So you get back the same function multiplied by some constant here. Okay? So this is for kinetic energy. Now it has its kinetic energy operator eigenfunctions. By the way, we have the whole system of eigenfunctions usually. because it's not only a single eigenfunction for a particular operator. There could be many eigenfunctions for, actually infinite number of eigenfunctions for a particular operator. Okay. Now, the most important point here is, in order to predict the results of experiment done on the property that corresponds to the operator, the results of the experiment can only come as eigenvalues corresponding to the eigenfunctions related to this operator. Okay, so in quantum mechanics we have a relation: any property, operator, eigenvalues. Eigenvalues, and that is essentially theoretical prediction for results of experiments. Results of experiments on that property. Okay. So this is all kind of theory up. So this is theory. And the down part is experiment. Right? So in this course, what I'll be showing you a lot is how do we do this part. Okay? So how do we go theoretically about predicting the property that then can be measured in experiment. Okay? That's the idea. Now, going back to this scheme, grand scheme, you can see that, okay, well, there is a property T, operator, eigenfunctions, eigenvalues, and eigenvalues are numbers. That's what you see in experiment, right? When you measure something, it's you only measure numbers. You don't measure functions. You don't measure any other tensors or whatever objects, more general objects. You just measure numbers always. That's why it's so natural that eigenvalues are the only things that you can see in experiment. Okay, and that's why they are so important. Because if you're interested in property and want to predict that property, you need to know what eigenvalues are. Otherwise, there is no way you can predict what possible measurements could be, because then, yeah, you don't simply know what even the range of possible values could be if you don't know anything about eigenvalues. Okay, so that's why eigenvalues and eigenfunctions are so important in quantum mechanics, because they allow you to obtain the result of experimental measurements on the properties through such abstract things as operators. Okay. Now, of course, solving this problem is not easy. We will look at the particularly easy cases, of course, in this simple introductory course. But now, just to complete the picture, in reality, we think of a quantum system as something that is described by the wave function. And now the question is this wave function that we are dealing with, is it an eigenfunction of the kinetic energy operator? Is question clear? Is clear what I'm asking?
Yeah.
Okay. So what would be your answer? So it's not clear then. The question is, the wave function that describes the system, right here, is an eigenfunction of the kinetic energy operator. In other words, if I have kinetic energy operator, because I'm interested in predicting kinetic energy of the particle, right? Then I put psi xt. T is not very relevant because small t is not relevant because large t doesn't really affect small t. Then the question is whether this is some constant multiplied by function. Yeah.
Yeah, it depends on the wave function.
That's right. It totally depends on what this function is. And who dictates what this function is? Well, it depends on the system, that's true. But also, this equation, right? It defines how the function that you may start with at t0. So you say you decided to look on the electron, and at t0 you prepare the electron in a certain wave, in a certain state that is described by this wave function, right? And that t will be 0 then. It's only like a distribution in space, right? And then you went for your apparatus, say, to measure the kinetic energy, but the electron will not kind of stop moving or stop doing anything, right? It will not stay still, wait for your apparatus to come so that you can measure. Electron will behave according to this equation. That's what Schrödinger taught us, is that, and there is an h bar here, right? So there is this equation that tells you what the wave function will be at later time. Now, say you brought your apparatus at some time, t, you got your wave function, you start measuring the kinetic energy of your electron, and the question now, what do you get as a result, depends on whether the function you are measuring is actually an eigenfunction of the operator or not. And there are two answers: yes, no, right? And I'll show you exactly how to predict the results of the measurement in both situations. Now, in case when the answer is yes, that's the simplest situation. If your wave function is an eigenfunction of the operator you're interested, you get your eigenvalue, and that lambda will be the result of the measurement. So you may even forget about your apparatus, you don't need it anymore. Quantum mechanics predicts what the result will be. Or you, of course, can still measure it, and you will get this number. Yeah?
So what instant in time would that be the result?
The time here, I haven't defined that time, but in this particular case, if your wave function is changing with time, so that at some time it is an eigenfunction, and at later time it may not be an eigenfunction of operator, then answer to this question will depend on time, right? So now, when I'm considering the yes branch, I'm considering the time when this function is an eigenfunction. Okay? So generally, time may change the answer to this question, but well, you need to just consider that situation. We will deal with this situation a little bit later when I'll teach you how to solve this equation in some relatively simple situations. But right now, just time is at this is fixed, but haven't yet determined. Okay.
So when you say that lambda is going to be results, in the scope of looking at kinetic energy, let's say we take some electron, we're trying to create a function, and we're trying to accelerate it to some other point for whatever reason.
Yeah.
We can measure the lambda in experiments as like a change in energy, as like a change of acceleration, a change of velocity. Like how are we connecting the actual experimental, like instrumental results to our prediction? Like, does our prediction have units? Does our prediction have a probability distribution? Like, how are we interpreting this lambda?
Okay. Well, first units, right? Units of lambda is this is units of energy, right? Okay. And as for the distribution of results of the measurement, that's kind of a beauty of this case, yes, that there is no distribution. It's when it's yes, when the wave function is an eigenfunction of the operator, then you can measure it And in any case, the result will be corresponding eigenvalue. Okay? Of course, in the real, like, not in a hypothetical experiment, but in a real experiment, there is, of course, always experimental error. And if you make exactly the same copies of the wave function, and exactly at the same time you measure you measure it, then there will be some distribution, right? But that variation is not, it cannot be predicted by quantum mechanics. It's a variation that is coming from the experimental error, or essentially the way the apparatus was different, maybe slightly, for these copies of the system, right? So that's beyond our consideration. The distribution that will be of importance for us is going to appear in the null case. Okay, because null case is more interesting. And also more general, because once we are done with null case, you will see that applying the null procedure, you can obtain this result as a particular case. Okay, but I still like to split it in two, because this one is very easy. All you need to do is to check if you are given a wave function and you are asked about the result of the measuring of certain property, you need to find an operator and check that operator acting on the function gives you constant times function. Okay, very clear. Now the null case. Null case is tricky, but not very tricky, because okay, so this is not the case, right? So let's write T psi is not equal lambda psi. But we know still that T has functions which are different than our function psi. And these are the right functions. They are eigenfunctions, right? And presumably we know them for every operator. That is quite optimistic to say that we always know the eigenfunctions. But for purpose of just describing the procedure, that's a kind of necessary assumption. More than that, you can prove, it's one of the postulates of the quantum mechanics, that any observable has an operator that has a complete set of eigenfunctions. Now, what is this word complete? What does it mean? Well, it means that any function psi, whatever function you want, can be expanded as a, you can think of as like a Fourier series, or just an expansion which can be potentially infinite from, say, 1 to infinity over the functions which are eigenfunctions for the operator of interest. Okay? So now this is kind of the reason why we can treat the general situation where function psi is not an eigenfunction. We can always connect any arbitrary function with eigenfunctions. Okay? So this is very nice and key relation. Now it's you probably studied or heard about the Fourier series, and this is one kind of more general kind of case of the Fourier representation, because in Fourier series these functions are cosines and sines, while here it could be something else. Yeah.
We're expanding it to the linear combinations of the function, right?
Right.
One thing I don't understand is, like, I understand how you can get linear combinations of a vector.
Right.
Because you have the unit vector and use that, right? But how do you get, like, the equivalent in functions like a unit function?
Yes. It's a very good question. And that's actually the reason that this is the part where I want to connect it to the previous lecture. To my taste, in previous lecture, there was this switch to vectors, right? And there was not much explanation why did we switch to vectors and why considering vectors is so useful to study quantum mechanics. Oh, it turns out what we do with wave functions will be algebraically absolutely the same as the operations that we are doing with vectors. Because imagine you have an arbitrary vector v and you want to present it as a linear combination of basis vectors. And then there will be components of this vector v multiplied by the basis vectors. And the only difference will be just that the space will be finite space, right? So say we have three-dimensional space and there will be three basis vectors, right? Now, this is the situation, E1, E2, E3, that's our vector v, right? The question now, how do we find these numbers? Okay. The answer is very simple. All we need is to introduce the concept of inner product, right? So with inner product, what we do, we take any vector, any basis vector, let's say ek, and we make an inner product with v. You will see in a moment how this will help us, because inner product has this linear property. We can substitute v by the expansion. And we don't know yet what the vi is, but we still can formally manipulate this expansion. Right? So because inner product is a linear kind of structure, we can put the sum outside. And what we have inside is ek, ei, and then the components, they can also be put outside of the inner product because they're just constants, right? Now, what are these guys? Inner product of two basis vectors, essentially, k and I. Usually we choose basis vectors which are so-called orthonormal. What does this mean? That means that the inner product between the basis vectors is either 0 or 1. And it's 0 when k is not I. And it's 1 when k equals to I. Right? So that's what orthonormal is. And in our derivation, we will frequently use so-called delta Kronecker symbol, delta ki, which is exactly what I said. 0 when k not equal to I, and 1 when k equals to I. Right? Now, if we put instead of these inner products the delta Kronecker, then this sum will be sum of this delta Kronecker symbols multiplied by our components. Now, k is fixed, so k is one number out of 3. So let's say k is equal to. Then I equals 1 will be gone because this delta will kill that term. I equals 2 will survive because it's delta 2, and it's 1. Now I equals 3 will again be gone because k equals 2 and I equals 3, so this term will be 0. Now what we end up with is v, which has I exactly the same as k. And that's the only survival of this sum, right? So we got the component of the expansion. How did we do it? We took a vector and we made the inner product. And the only condition we used here is that the basis vectors that we used, they were orthonormal, right? Now, going to the functions, we can do exactly the same thing. Now our functions are vectors. The coefficients are the components, right? So these are our basis vectors now. This is kind of analogs of EI, and this is the analog of vector V, right? And now you can ask me, all right, this is all good. How do I make this? How do I introduce inner product with functions? That's the only question we need to answer, and then the rest will be the same, right? Because once I introduce the inner product, I can do the same types of operations and find these coefficients, which will essentially complete the definition of this expansion, right? And this approach to the functions as vectors, I think that's the first time was introduced by Fourier, and that was a very big step, because just think about it. You have some random function psi, and you're trying to expand it as a linear combination of sine and cosines. How do you do that? You need to find the coefficients. And you can think of this problem as like probably the closest would be in Excel. You have a bunch of data, and you're trying to fit this data to some polynomial, right? And then you're trying to fit the coefficients so that the polynomial of certain degree will be the closest to the data you obtain from measuring something, pH of some solution, all right? And this is kind of messy and numerical procedure, which not always gonna give you the unique solution, and has many problems. Now, approaching the same problem by considering functions as vectors is much cleaner and nicer approach, and all it requires is introducing the inner product between two functions. Now, how do we do that? Let me just formulate the answer, and then I will explain why this answer makes sense. The inner product between function psi and, well, in quantum mechanics, people use so-called Dirac notation usually, and that's why instead of comma and round brackets, they use angular brackets and bar. For now, this is just notation. It's essentially the same inner product idea. And that inner product is equal to integral over the whole space, minus infinity to plus infinity, function psi with a star conjugated x. Oh, it has t, but t is not important for now because we integrate only the spatial part. And f of x. Also, I'm kind of sometimes using physical notation for the integral, where they like to put the integral, then dx, and then what the integrand is. So it's the same as putting dx at the end. Doesn't really matter. All right? So this is the definition of inner product between the two functions. Okay? Now, why does this make sense? How do we define the inner product between two vectors? Say you have V, U, yes, and we know their components. That's right. But if they're different, it's not the length, it's more like an angle, right? That's the geometrical idea between the inner product. If you divide the inner product of V and U by the length of V and the length of U, that will be a cosine between these two vectors, right? Now, how do you formally define this? It's just a sum over all components of V multiplied by corresponding components of u. Okay? Very simple. Now, if these numbers, v and u, they can be complex, in order to avoid having length that is non-positive, you need to have star for the first vector. Okay? Now, this is not very obvious, and I can simply illustrate this. Say you have a vector I0. That's a vector, say, v. I0. Now, and you want to calculate what's the length of my vector. So I do inner product vector with itself, and then I'll take a square root, right? So now, if I do this according to this expression but without star, then it will be a square root of I times I plus 0 times 0, right? First component I multiplied by the first component of this guy, I, 0, 0. So this will give me minus 1, and the square root of minus 1 will be I, right? So I will get the length of the vector, which is imaginary. Vector itself has imaginary component, but length always positive. Okay? So this is no good. Now, if I fix this by conjugation of the whatever I have in the first vector and the left vector, then I star will be minus I, and minus I times I will give you 1. The square root of 1 will be 1. Length will be 1, which kind of makes sense because it's a kind of unit vector just with imaginary number in front. Okay, so that's why this star is important, to have length of any vector which is non-zero to be positive. That's how inner product is defined for vectors. You see, star here, like star here, so it makes sense. Now, vectors contain discrete number of components. Functions, on the other hand, they have infinite number of components, right? Because you can think of a function as essentially, how do we plot function? We know what function will be at 1, at 2, at 3, at 4, other values, and then there will be the value of function in these points, right? And potentially the number of points is infinite. Now, you can apply the same idea that the function is really a vector, very long one, right? Because it has so many components. The f will be the function with all these components, where the components will be f of x in a particular point, f of xi. Now you need to sum f of xi with the corresponding components of the psi vector. And there are also infinite number of them. Now what helps is to substitute sum by integration, so that the sum will not be infinite, and the integration kind of solves the problem of infinite sum. How does it solve it? It multiplies every product by the small piece of argument, dx. And that's what makes the integral finite. And usually with the functions we're dealing with, it's finite. The integrals here will be always finite. There is algebraic reason for that. With any inner product, and this case is not separate, this integral always smaller or equal than integral over psi and multiply square root of this integral multiplied by square root of this integral, right? So that's so-caught Cauchy-Bunyakovsky inequality, where it shows that any inner product between two vectors or two functions will always be less or equal than product of corresponding inner products between the same functions, which is useful because we know the functions we're going to work with, they're L-square integrable. L-square integrable functions, they means that they're normalizable. So these integrals will be always close to 1. All right? And so this integral cannot be more than 1, 2, because these guys are going to be around 1. Okay? So now we introduce inner product. Now we can obtain these coefficients the same way we obtain the components of the vector when we know the basis vectors. What do we do? All right, so the recipe is very simple. We can integrate the function psi with f of an x, and then substituting psi with this linear combination, so n should be, say, substitute to some k. So k is arbitrary. And you will see at the end that we will obtain ck. By choosing certain k, you will obtain a certain coefficient out of this expansion. Right? Now, yeah.
Just wondering why you conjugated the function and not the side function.
It's the same idea as with vectors. You have a vector, right? And so what did we do with vector? We multiplied by the basis vector, right, from the left. But when we do this, the conjugation goes to the left component, right? That's why when we multiply by a function, it's the same as multiplying by the basis, taking inner product between the function psi and the basis function phi k. Right? So that's what I did essentially. Right? I took the function psi and multiplied from the left by and integrated with the function phi k. That's why conjugation goes to phi k. All right? The same way we obtain the components of the v by multiplying by basis vectors. Now here, what we have is we can take the sum outside of the integral, coefficients outside of the integral, and then inside of the integral we will have integrals of functions phi n, phi k, star x. And it seems like we ran into more troubles, but in reality we're not. We're very close to the end, because these integrals are one of the simplest integrals you will take in this course. They are integrals between so-called orthonormal functions. Well, functions are like vectors. They can be orthonormal. Well, what does that mean? Well, say function can be like this, another function can be like this. It doesn't look like two vectors which are orthonormal, right? But they are, because what means orthogonal, right, is that the inner product between these two functions should be either 0 or 1, depending on whether k equals n or k not equals n, right? So functions are orthogonal when the integral between them will be 0, right? And it turns out that all the observables in quantum mechanics, they have functions which comprise the complete set of normal functions. Okay, so all these guys that are eigenfunctions of the operators we will be considering, they have this nice property that unless they are identical, n and k, the integral will be always 0. But if they are identical, the integral will be 1. That can be shown. And so if that's the case, then we get the delta Kronecker and k in this sum, and that delta Kronecker essentially kills all n's which are different from k. And k is fixed. It's arbitrary, but it's fixed. And so this whole sum ends up being just ck. So that's the recipe. How can we obtain the coefficient? This one? This one? It's a C subscript n. Right. Okay, so why is this such an important result? It is a very important result because these coefficients will be very useful for us. We are still considering the null situation, right? We are very close to the summary of the null situation. In the null situation, then the prescription is the following: how to predict the result of experiment. We have, say, wave function, and we have an operator. Operator has its own eigenfunctions, and our function is not one of the eigenfunctions. But these eigenfunctions can always be used to expand whatever functions we have as in linear combination. And now we know the way to find the coefficients in this combination. So this combination is fully defined for us now, right? Because the coefficient Cn is nothing but inner product of function n with the psi, which is just an integral, this one, right? So we know how to find the coefficients. Now the result of the experiment will be still eigenvalues of corresponding operator. Now, though, we have many of them, potentially. It turns out that any of them can be a result of the experiment, but the probability to find in experiment this value, lambda n, is equal to Cn squared. So that's the probability. Okay? So that means that if we have some wave function psi and it's not an eigenfunction of the kinetic energy operator, we still can expand it in a linear combination of eigenfunctions. And if we start measuring the what is the kinetic energy for our system, we will start getting random results, right? Well, they're random in the sense that we know what they are coming as an eigenvalues, but we cannot predict what is the particular value of lambda n which we will be getting in the next experiment. We cannot do that. Quantum mechanics doesn't know how to do it. All it knows how to do is to predict what's the probability. Okay? And now you can see the probability is related to this coefficient. Coefficient itself can be complex. That's why we have an absolute value squared, right? So this value is always between 0 and 1. It cannot be complex. And it also has the influence of what the wave function was. Okay? Yeah.
Is that Cn the same one in the equation above, or is that Cn the same thing as the Ck? So we solved for Ck, we solved for the coefficients, right?
Yeah.
So
I think CK was just specific to that integral, like implementation. Like CK is just one of the CNs that we can get.
Yeah, that's okay, I wasn't planning for that, but let me explain. Okay, when I say K, this is just an index. It can be anything, right? And when I say N, it can also be anything, right? It's just two letters that are used to represent different numbers, right? Generally. And the only difference here is that the K is some fixed number. So say someone has in mind a particular, or someone is interested in a particular coefficient, right? But this is prescription to find CK, and K can be anything, right? So once you kind of figure out what K you want, you go through this procedure and you obtain that CK, and you go to the next one. Now, in this derivation here, I use CNs without knowing them, right? That's fine, because that's just a formal consideration. And here n was a running index. N was from 1 to potentially infinity, right? And so here is the same, 1 to infinity. And at the end, I obtain CK. Now here n is equivalent to k, pretty much. Can be anything. Any particular n or any particular k, yes?
When you get the CK, it's going to be, it's the result of an inner product, right?
You're referring to this?
Yeah.
Mm-hmm.
Like I'm thinking about practically when we're actually trying to achieve a result here. Is CK, because it's like one arbitrary fixed point, is it going to give you a function to describe how the CM changes? Or is it going to be looking at one specific system and instant, and that's just one eigenvalue of many? Like, does it produce a series, or does it produce one uniqueness?
It produces a series.
Okay,
Yeah.
that's what I think.
But I understand that this case, yeah, I will consider this with a specific example, not today, but next lecture we'll start with a specific example for actually both situations. And for specific example, what we need, well, we need to define what the functions are, what the eigenvalues are, and what the wave function we're dealing with, right? So once we have operator, its eigenfunctions, eigenvalues, and the functions that we represent our system with, then we're good to go and predict the result of the measurement experiments, okay? Now, just to conclude, why no case is more general and it can predict the yes situation? It's because this essentially can, in the situation when psi is one of the f functions, say fn, or if you like f1, right, for the concreteness, right? Then this inner product will be only non-zero if n equals to 1, right? Because all these functions are orthonormal. So that means C1 will be 1 because it's the inner product of F1 with itself, right? And C1 squared is also 1. So the probability of finding lambda 1 in this case will be 1, and that's the only result out of the measurement you can get, right? And that in a situation where our function was an eigenfunction from the beginning. Okay.
So if the probability, if the probability is 1, then that's the yes scenario, right?
There's no other choices, yeah. Right. So these coefficients, essentially, if you have many non-zero coefficients, then you have uncertainty, so-called. And that's what we're going to consider eventually also in this uncertainty principle. Uncertainty comes from the fact that you have many coefficients which are all non-zero, but if you have only one coefficient which is 1 and others 0, then it's all very certain. Probability 1 is only for one event, and there's no other event that competes with that. Okay? Any more questions? No?